Hello everyone, and welcome back to another tutorial video. This is the second in a series of videos covering problems on Laplace transforms. In this video, I want to go over problems from section 7.2, which asks you guys to use the Laplace transform to solve specific initial value problems, or IVPs as we like to abbreviate it. In this video, I'm going to be covering exercise 3 from section 7.2, which is as follows. We are given the differential equation x double prime minus x prime minus 2x is equal to 0. Please note that I believe in all of the problems in this section or of this type, you will be dealing with linear differential equations with constant coefficients. Okay, so we have that set up. And then we are, because this is an initial value problem, we are also given the initial conditions. X of 0 is equal to 0, and x prime of 0 is equal to 2. Now, the process of doing this is always the same. So the first step is to take the transform. And use linearity. Now, what do I mean by this? I mean that we're going to take the Laplace transform of both sides, so that we get that the Laplace transform of x double prime minus x prime minus 2x is equal to the Laplace transform of 0. Now, of course, the Laplace transform of 0 is equal to 0. And this Laplace transform on the left-hand side can be split up using linearity. So this gives us that the Laplace transform of x double prime minus the Laplace transform of x prime minus 2 times the Laplace transform of x is equal to 0. All right, we've completed step 1. Step 2 is going to be to use the formulas. Let me find them. Aha. Yes, they are the formulas from theorem 1 from theorem 1, yeah, and from the corollary in section 7.2. And these tell you how you can work with Laplace transforms of derivatives. Now, what this theorem tells you is the following. If you take the Laplace transform of a derivative, say f prime of t, this is going to be equal to s times the Laplace transform of f of t minus the value of f at 0. Okay, so now we're going to apply this here in two different ways. Actually, in fact, let me write a second sort of equivalent version of this. If you just add a prime everywhere here to all of the f's that you see here, you'll see that you can very easily get that the Laplace transform of f double prime of t is equal to s times the Laplace transform of f prime of t minus f prime of 0. We're going to use both of these things to proceed with this problem. So I'm now going to substitute, and I'm going to try to color code as I usually do so that you guys can clearly see what I'm doing. Also, please be careful, don't forget the parentheses in this section. Instead of x double prime, we are going to get s times the Laplace transform of x prime minus x prime at 0. And all of this is from the red. Next up, we have minus, and a parentheses again, and this one will be from the blue. So instead of the Laplace transform of x prime here, we are going to have s times the Laplace transform of x minus x at 0. And all of this, once again, is from the blue. And last but not least, I'm going to have to continue on a new line here. This is minus 2 times the Laplace transform of x is equal to 0. Okay, now we are not quite done yet, because you'll notice that I still have the Laplace transform of a derivative here. So I'm going to have to use that blue substitution once more. So let's do that real quick. And we will get the following. We will get that s times the Laplace transform of x minus x of 0 minus x prime of 0 minus s times the Laplace transform of x plus x of 0. I've multiplied out that negative sign here, minus 2 Laplace transform of x is equal to 0. And once again, in this case, I used the blue substitution right here. So you can see what I substituted there. All right, let's start simplifying a bit here. We've got s squared times the Laplace transform of x minus s times x of 0 minus x prime of 0 minus s times the Laplace transform of x plus x of 0 minus 2 times the Laplace transform of x is equal to 0. All right, we are now done with step 2. It's a little bit tedious, but hopefully you guys will pick up on this pretty quickly, and this is not all that difficult. All right, step 3 is very simple as well. Factor. Okay. So very specifically, what I want you to factor is to factor out the Laplace transform of x here. And this is going to give the following. We're going to get that the Laplace transform of x. And here, what do we have? We have an s squared. We have a minus s. And we have a minus 2. Okay, and then what are we left with? We are also left with minus s times x 0 minus x prime of 0 plus x of 0. And all of this is equal to 0. And last but not least, step 4 is to plug in the initial conditions. And so this is going to give us that the Laplace transform of x times s squared minus s minus 2 minus s times x of 0 is 0 minus x prime of 0 is 2 plus x of 0 is 0 is equal to 0. Okay, now hopefully you see here that, of course, this term will go away, this term will go away. And so what I'm about to do now is I'm going to clear the board and resume from what we've done here. But I want to point out that what we've basically completed so far is the first main stage, I will say, of solving an initial value problem by using Laplace transforms. What I've done here is I have transformed the differential equation we started off with x primes and x double primes and so on and so forth, into an algebraic one. What I'm going to do after this, in the second main stage, is going to be to solve that algebraic equation. That should not take very long. So let's get right to it. Alright, so what we were left with was the Laplace transform of x times s squared minus s minus 2. And I believe we had a minus 2 is equal to 0. Yes, that is what we had. Alright, so in the next phase, I believe we're on step 5 here. Is to solve for the Laplace transform of x. And this does not take very long at all. And here we will quickly see that we get that the Laplace transform of x is equal to 2 divided by s squared minus s minus 2. Alright, this brings us to the last stage, I should say. The what's left to do here. What's left is to find the inverse transform. And I'm not writing this as step 6 because there's multiple steps that are involved with this. And specifically with several of the problems, especially the ones that end up looking something like this, where you have some sort of big fraction with a polynomial on top and on the bottom, in the numerator and in the denominator. Very frequently, the very first step that you need to take to find the inverse transform is to basically just get partial fractions. Now, hopefully, partial fractions is something that you guys are relatively familiar with, but I will still try to go over this in relative detail here. I will probably make another tutorial video that goes a little bit more in depth on the partial fractions idea, so I might gloss over some of that here. So what we're going to do in this phase is just do partial fractions. So for partial fractions, the next step is to factor the denominator. And we see that we have the Laplace transform of x is equal to 2 divided by, and down here we have s squared minus s minus 2. And you can see that this factors into s minus 2, s plus 1. And once you factor the denominator, you can set up the partial fraction decomposition. And we'll see here that this is going to be equal to a divided by s minus 2 plus b divided by s plus 1. Alright, now that we've set this up, step 7 is to put on common denom. And at this point, it doesn't really matter what the denominators are. So I'm just going to write that here we have 2 over denom. It's going to be equal to a needs to be multiplied by s plus 1. So here we're going to have a times s plus 1 over the common denominator. And then b needs to be multiplied by s minus 2. So I will do the same here. And this should always be the case when you get to this point. You should have, obviously, common denominators everywhere. And because you have the same thing dividing everything, you can just clear it entirely and make your life quite a bit simpler. So this is going to give us that 2 is equal to as plus a plus b times s minus 2b. Now step 8 is to set up your system and solve. So there's plenty of ways to do this. You can plug in specific values of s if you want, or you can just do identifying coefficients. There's all sorts of ways to do this. But in this case, and again, I will go into greater detail into how I did this step in particular in a future video covering section 7.3, which goes much more in depth on partial fraction decomposition. But here you will see that we get here that, let's say we have a plus b for the s's. So we're going to get a plus b is equal to 0. This is from the s terms. And we'll get that a minus 2b is equal to 2 from the constants. All right. Again, I don't want to take too much time in this specific video. Hopefully you guys know how to solve a system of equation like this. So I'm just going to state what the solutions are going to be here and proceed. So the solutions here are, I believe we should get that a is equal to 2/3 and b is equal to, I believe, negative 2/3. All right, we've gotten the partial fraction decomposition. So I'm now once again going to clear the screen and proceed with the final major stage. Once the partial fraction decomposition is complete, well, I guess it's not the final major stage, it's just the finishing up the process of finding the inverse transform. We've got the partial fraction decomposition. We need to find its inverse transform. Okay, so what did we get? We got that the Laplace transform of x is equal to a, we said was 2/3 over s minus 2. And b we said was negative 2/3 over s plus 1. All right, step, I believe, 9. Find the inverse transform. Or I guess more accurately would be to be just taking the inverse transform of both sides. We get the inverse transform of the transform of x is, of course, just x. So here I'll even write x of t. And this is going to be equal to 2/3, or before we get there, this is going to be the inverse transform of 2/3 over s minus 2 plus negative 2/3 over s plus 1. But thankfully, the Laplace transform and the inverse transform as well is linear. So we can pull things out and split things up just as we would with the transforms themselves. And get that we have 2/3 of the inverse transform of 1 over s minus 2 minus 2/3 of the inverse transform of 1 over s plus 1. And this is our x of t. All right, this leads us to our final, step 10. Here we go. Just plug in known inverse transforms from table 7.1.2. So, which one am I using in particular in this case? Well, both of those two fractions have actually the same format, and I will apply the same result from these. We know that the transform of e to the at is equal to 1 over s minus a. In other words, and maybe I should do this in a different color, I'll use blue here. In other words, the inverse transform of 1 over s minus a is equal to e to the at. So using this, finally, after all this work, we get that x of t is equal to 2/3. Now the inverse transform of 1 over s minus 2, in that case we'll see that a has to be 2 in that case. So this will be 2/3 of e to the 2t minus 2/3 of e when you have s plus 1 in the denominator. That means that a is -1, so this will be e to the negative t. And we are all done. Alright, very lengthy process, I'm aware. That's mostly because there's a pretty significant number of steps. Not that necessarily any particular one of those is particularly difficult, I think. With some practice, hopefully you should be able to get this down. And again, for the whole partial fractions section, I will go into more detail on that in a future video, because partial fractions is one of the bigger concerns of section 7.3. Alright, as usual, please let me know if you have any questions or if there's anything that I missed in this video, and I will catch you guys in the next tutorial.